All right, everyone is back, right? Okay, all right, let's start. So, so we talked about SMART and the motivation for considering SMART as opposed to stitching information evidence across different trials, one-stage trials. So, in general, these are multi-stage trials, not just two. It can be more than two, with the goal to inform the development of TTRs, the full sequences. And note that here the same subjects participate throughout the different stages, and each stage correspond to a treatment decision. Each stage the patient is randomized to one of the available treatment options, and the options that we consider at each stage can be restricted if necessary based on ethical grounds, depending on the intermediate outcome and of the treatment history. So, as a concrete example, if you were given treatment A earlier and you did not respond to that one, you would not be re-randomized to the same treatment option. So, it's not left to pure full randomization alone. So, if you have not responded to something before, you will not be re-randomized, or if you have experienced side effects and so on, you would not be re-randomized. So, that kind of adjustments can be done. So, it's not like randomization and blindly re-randomization, right? So, that is one aspect of it. Okay. So, just to trying to list the gains and losses of SMART. So, first important thing is ability to detect this delayed effect, which we talked about earlier. It can also be diagnostic effect, not so much about the treatment effect, so to speak, but in a way, sometimes in certain situations, a treatment given early on may help you better decide on the second stage treatment. First stage treatment in itself may not have a very high effect in terms of therapeutic effect, but it can help you diagnose the condition better. It might improve the symptoms in a way. The symptoms might express better, and then it might help you in the long run to give better treatments in the second stage or in later stages. So, that is what is meant by diagnostic effect. So, SMART can incorporate these ideas. And then other concept is generalizability. If you're familiar with the trial design literature, people think about this generalizability option. Which context can we generalize our evidence from the trial, right? So, usually in a standard RCT, we want to minimize heterogeneity, and in that case, the inclusion criteria for the trial participants is narrower. Whereas here, we accept the fact that people are different and people will respond to different treatments and so on, and there are different pathways. If they are non-responder to the first line treatment, you might give something else, re-randomize to something else and so on. So, you are actually embracing that variability. You are not trying to avoid that variability, and by doing that, we can potentially capture a broader audience, and that means you might have greater generalizability compared to a standard RCT. And other than that, there is another big advantage. Well, these are all conceptual, right? So, it's not from data you cannot show yet, but basically better recruitment and retention potential compared to a standard RCT. So, for those of you who work with clinical trials, actual implementation and so on, there are always issues with recruiting people, right? Because people do not like to be randomized to treatments. They want definitive treatment. So, randomization, even though scientific community values it highly, people, and we cannot blame them. I mean, if we were the patients, we would not probably like it either, right? So, that's the problem with recruiting people in an RCT. And but if you also the retention, right? Sometimes if you are randomized to something, even if you agreed to that, if at some stage, if it's not really working, you are experiencing some side effects, or it's too burdensome on your lifestyle, people drop out or people do not comply, right? So these issues are always there. Now, by doing a smart, what you are doing is basically telling people during the informed consent process, you are telling people that, okay, we are randomizing you to something, but if it doesn't work for you, if we adjudge you as a non-responder, you might get something else. You might be re-randomized. Again, randomized, but re-randomized to something else, and so on. So that means even in a two-stage smart, you will have a second chance of getting something that might work for you. And if it's more than 2 stages, then that chance increases that eventually something will work for you, even though you are part of an experiment. So that thing, telling them that thing upfront, the participants, it might have a positive effect on the recruitment, right? They might feel that, okay, it's not like at one shot you go and then if it doesn't work, you have to drop out. No. So you have a second chance. So that might also help people engaged and improve the retention, etc. So that's one very good attractive feature. That's quite ethical, and from a practical point of view, that's very attractive. But there is no free lunch. There is always some cost associated with it. Generally, it would be more expensive, longer follow-up time. You have to maintain that trial for a longer time, and then comes the question about sample size, something that worries everyone. So if you really want to power your trial to compare the whole sequences of treatments, then it's a problem in the sense that it will inflate the sample size, right? But then there exist less expensive alternatives to power smarts, and in fact, as I have some slides later. So basically, it can be exactly same as an RCT, depending on how you choose your primary research question, and so just to avoid that situation. So the bottom line is, it does not necessarily have to be larger. But if you really want to power your comparison of different treatment sequences, then you have to pay a bit more. You have to recruit more. So that will increase the budget of the trial. But then, if you can leave that question about comparison of the different treatment sequences as secondary, do not fully power it, but maybe focus on the first stage treatment, for example, treatment comparison, for example, and power the trial according to that, then the sample size requirement will be exactly same as the standard RCT. So it does not necessarily increase the sample size. It depends on what you want. If you want to know a lot more information, which is basically the full comparison of the treatment sequences in a fully powered way, then of course you have to have more budget, more people. But there exist less expensive alternatives. And of course, the other disadvantage, if you view like that from a practical trial design perspective, that it includes complex methods for planning and analysis, and not the traditionally trained statisticians. Not everyone can know it upfront. So either you need someone who knows these methodologies, or at least someone who has the time to learn new methodologies. So that's a practical consideration. And then, of course, you might face this hindrance from funders, because they also want to have something very widely known, but this is still relatively new. So there needs to be ways, very good grantsmanship to convince people to fund such trials. And one way to do it is basically, keeping the sample size requirement same as RCT. That's one way to avoid rejection from funders. Okay. Yeah. Or AI. That's great. Yeah. Okay. Sure. That's right, yeah. Yeah, I'll come to that. I'll come to that, yeah. I'm still talking about the design aspects, yeah. Yeah. Okay, so just want to make a few distinctions, some remarks about distinction of SMART from some of the other trial designs, because that may cause confusion. And so those of you who are familiar, maybe not the computer scientists here, but some of you who are trained in the traditional stats, biostats. So SMART is not a crossover design. Crossover design, even though operationally it might look similar, conceptually they are quite different. So first of all, unlike SMART, crossover trials aim to evaluate standalone treatments. They are not about sequences. They want to estimate effect of A versus B, not A followed by B followed by C, etc. So even though the operation is that you give A and then B or whatever, right? So the aim is different. Then unlike a crossover trial, treatment allocation in a SMART is typically adaptive to a subject's intermediate outcome, right? So responder versus non-responder, based on that intermediate outcome, you are reassigning treatment. Whereas in a crossover, sequences are fixed. It doesn't matter how you respond. And then crossover trials attempt to wash out the carryover effect, which is basically the delayed effect. But here we are specifically trying to capture it. So fundamentally, these are very different trials, even though they look kind of similar. And I try to address these differences proactively, because previously in many occasions during my talks, people ask me whether this is similar to crossover and so on, and because that creates confusion. So that's why I tried to address it upfront. Okay, now SMART versus usual adaptive trials. And so they are also, again, different from the usual adaptive trials. The key distinction is within subject versus between subject adaptation. So in a typical adaptive trial, outcome adaptive trial, the randomization probabilities can change during the course of the trial, right? You still have an RCT, A versus B, and maybe you are randomizing between them evenly, half and half. But as the trial progresses, as you accumulate more data, then you are shifting to one treatment or the other, depending on how they are performing based on early data accumulation, right? Relative success of the already recruited patients on each of the treatments. And the adaptive trials typically aim to reduce the number of trial participants exposed to the inferior treatment. You want to disseminate quicker to the participants the better looking treatment, even though that may not be statistically significant yet. But as you see the trend, you are changing the randomization probabilities according to that. And adaptive trials are most useful for examining questions where the outcome follows fairly quickly after treatment, or the recruitment process is relatively slow. Only then you can apply this kind of setting. So these are classical adaptive designs. The terminology is very broad, but this is the sort of the main way of doing it. And Joseph, this is the dynamic experiment, right? Yeah. Multi-arm, right, yeah. So but then SMARTs as presented so far are fixed trial designs, while randomization probabilities may depend on covariates. For example, the responder, non-responder, maybe you can think of it as a covariate, and based on that, it can change, or you can incorporate other covariates as well. So that is there, but the probabilities remain constant over the course of the trial, right? It does not change as such. So that's the distinction. But again, I will come back to something where both these ideas, SMART and adaptive design, those can be combined together. I'll come back to that. Okay. So now the question is, okay, we talked about it conceptually, but are there real trials, right? So I mentioned this ADHD example, but without the trial thing, I just presented it as different treatment scenarios. But this is actually what happened. They actually randomized people according to those different pathways, and with a primary outcome of teacher-rated impairment rating for the ADHD children, and that's a continuous outcome. And there are some more studies, schizophrenia, depression, in these two contexts, KT and STAR-D trials. These are very classical SMART studies. Then there has been some studies on different cancers, prostate cancer, leukemia, etc. Several trials conducted at MD Anderson Cancer Center. Smoking cessation trial, something I worked on before. This was done at University of Michigan. In fact, I'll talk about a little bit of that trial analysis. And then alcohol dependence, lot of behavioral examples actually. And you can get a lot of examples, more recent examples following this website of the Methodology Center at Penn State University. They have a full list of things that they have helped conduct. Okay, so some of the principles, primary and secondary hypothesis question. So here the thing is, you have to choose important questions for primary as primary hypothesis that can also help in the development of the DTRs, and you have to power it according to that primary hypothesis. You cannot expect to power the trial for every single hypothesis or every research question, right? That's standard even in RCT. But here it's more so. You have to think. You have to proactively address that and convince the funders. But we choose secondary hypotheses that further develop the DTR and use randomization to eliminate confounding. Trials not necessarily powered to address these questions, but the argument in the grantsmanship could be that still better than post-hoc observational studies. You still and try to answer a lot of questions based on post-hoc data without randomization. But here, even though it's not fully powered for every single comparison, you at least have the randomization. So you still eliminate the confounding that is present in observational data. So that can be a strong argument for why you can still consider underpowered comparisons for some questions. And then the underpowered randomizations can also be viewed as pilot studies for future full-blown. That's one way to, avoid that problem and convince the funders. You can say that, but I'm still not talking about analysis. I'm only talking about design and how to convince funder, how to get these things done, right? And yeah, so from the funding perspective, it may be more feasible to design the standard 2-arm trial as a primary goal, and then the second stage or third stage kind of randomizations as secondary. I think that might be one way to convince funders. Yeah, okay. And then comes the question about tailoring variable. The responder, non-responder is one example of tailoring, but you can have other options. And but you don't want to make it too granular. If you make the trial design too granular, then it becomes practically very challenging to implement such a trial and ensure fidelity with all the plans and so on. That's a mess. So the recommendation is that you restrict the class of treatment options by ethical feasibility and strong scientific considerations. Make it relatively simple, but you collect all the intermediate outcomes potentially useful for further tailoring, and that can be done at the analysis stage, right? And okay, and of course, I think some of the things that are specifically geared toward not this audience, but more towards the clinical audience is that the tailoring variable, the thresholds need to be very clearly defined a priori, specific definition of responder versus non-responder, and that should be same across all the treatment options, etc., etc. And that variable should be regularly available in clinical practice. And then sometimes, particularly in mental health studies, feasibility considerations may force us to use treatment preference as one tailoring variable. Ask people what kind of treatment you want or what things that you don't want. And based on that, you randomize, right? So, I mean, they might want to specify a class of treatments that they want or don't want. And you might re-randomize or randomize within that class. You restrict to that. Otherwise, you will lose people, right? That's not something you want. And this is something that they did in this study that I mentioned about depression. They actually took people's preference into consideration. Okay, I mentioned the terminology embedded DTRs. So by that I meant, I said that ones that are already there by design, not implementing these threshold parameters and artificially constructing a lot of, because that you can create as many as you want, the other regimes. But here the ones that are already in the design, so I'm specifically going through one by one. So just follow the red arrows here. That's one regime, we call it D1. D2 is now without this, now instead of this you follow this pathway, that's second. Third is this, and fourth is this, right? So basically here there are 4 embedded regimes. Okay, so simplified data structure, typically often people, and for the time being you can forget about baseline, really baseline covariates, right? And then A1 for that design, that example, you have B-mod versus medication. O2 is the response status, R equal to 1 or 0, depending on responder, non-responder. And A2 have all these options. This is the intensification, that's why I use plus, and this is the combination, the augmentation. And Y is the outcome. So you can just to keep it very simple, the way we can, but of course you can incorporate baseline variables and so on. Okay, and formally, if you want to write the different regimes, you can write this kind of a notation with R 1 or 0. So that means responders will have certain treatment, non-responder will have another kind of treatment. That's how you can write the, without going through the picture, you can write it like this. Yeah. Modification. Right. Yeah. That's right. Yeah. Because then non-responder means R equal to 0. Yes, non-responder means R equal to 0, right? So then the first term will go away, the second term will remain. You know, think like a mathematical notation. Yeah, to the power, yeah. B-mod plus is the intensified version of B-mod. Yeah? Okay. Yeah. So, so now the question is, how can we measure the performance of an embedded DTR? How can we compare 2 embedded DTRs in the SMART, right? Okay. Finally, so you have to first create the estimand, what we try to estimate. This is called value function in the reinforcement learning literature, and we also follow that terminology. So there's the mean outcome if the entire population follows a particular DTR, call it D, and we call this, we use the notation expectation of Y under D. And we just, for a moment, you recall the general data structure for the K stages, intertwined O's and A's, right? And then, you know, the pi j's, suppose the pi j's are used to allocate the treatment. So it's the actual randomization probabilities, how they were given certain treatments. And because this is a trial design and not an observational study, this is something that you would know. And under that structure, then you can write the data likelihood or joint distribution. We call it P pi, and that's the whole thing, right? So here, basically, you have the baseline information, the density, the probability density of that baseline information, then the randomization probability of A's given the O's, and then likewise you multiply from stage 2 to K, you know, all the observations, the density of the observations given the history and treatments before, and then the randomization probabilities and the final stage outcome. So it's just, you know, you have that intertwined O's and A's. I'm just writing the corresponding densities, the probabilities like that. So that's how you can write the full data likelihood. And so that's one thing under the data generation distribution. But then you can also, F1 is basically the probability density function of the O's or the baseline covariates, baseline observation. Yeah, what distribution? Yeah, what distribution? Yeah. Joint distribution of the, yeah, everything. So you have the O1, A1, O2, A2, etc., right? The whole data trajectory. And I'm just trying to write the probability distribution of that, right? And in statistics, we call it likelihood. And I'm just trying to make the connection, because so far we've been talking in plain English. I'm just trying to mathematize it. And similarly, you can also write the likelihood of the data under a different distribution, right? So for those of you who are trained in statistics, you know that you have a set of data. You can write that likelihood according to different probability distributions. And so here, for any arbitrary deterministic decision rules, may not be the randomization probabilities, but certain rule which are deterministic. Under that, you can also write the data likelihood like this. So where basically we use indicator functions to see whether the treatment actually allocated is according to the decision rule D or not. If yes, then there will be 1. Otherwise, this whole likelihood will become 0, right? So that's how we write it. And the distribution of the O's, the observations or outcomes, that remains same. But the allocation is done in a certain way. This is what it is done. But this is how we want to evaluate. For a certain decision rule, we want to see whether these things matches or not, right? That's how you can write the likelihood. And basically, you use this actually means expecting with respect to the distribution PD, even though the data were actually generated by p pi, right? So data were generated according to the randomization probabilities, but ultimately when you are evaluating regimes, you want according to a certain rule that's not randomized. So that's what this notation means. Even though the data were generated according to p pi, you want to do it by according to PD. Okay, I think I'm losing my audience a little bit because not everyone is a statistician. So those of you who are trained in computer scientists, you know about importance sampling, right? Do you? Yeah, so importance sampling is one way. So you have a certain things done, but then you want to do it in a different way. So basically that kind of adjustment is being done here. And because without that you cannot evaluate the outcome of a certain regime, because you have to change your data generation probabilities, etc. So that's what we are doing here. And those of you who are trained in statistics probability, you know that you can do this kind of a change through so-called Radon-Nikodym derivative in probability. And by doing that, you can still evaluate the outcome corresponding to a different distribution that was not used to generate the data. That's what it is. Okay, I think I'll skip that. So with that general mathematical background, you can actually, for any of the embedded regimes, you can evaluate the expected outcome under that regime. And this is done by that change of probability, this formula, this Radon-Nikodym derivative or importance sampling weight, etc., whatever you call it. By doing this weighting, you can evaluate, you can actually write it down for any specific smart design example. You can write it like that. So you just have to create that weight. And weight is basically inverse. This is basically the inverse probability weighting approach that is more commonly used in the trial design or causal inference. And in fact, people who are trained in survival analysis, you know about this censoring weight. So this weighting idea comes again and again in many statistical aspects. So this is just another weight, right? This is inverse probability weighting. And again, those of you who are familiar with classical sample surveys, this is Horvitz-Thompson estimator in statistics. So basically this weight is nothing but, see, this is an indicator function, right? So it is either 1 or 0. But what is below is that matters. Basically 1 over the randomization probabilities, the product of the randomization probabilities. So you upweight or downweight certain people based on how they were randomized to certain things. And specifically, responders will get a certain kind of treatment and non-responders will be given a different kind of treatment, because the non-responders got what they got with a certain probability, and responders got what they got with a certain probability. The responders always get something. In this example, responders typically get the same thing as they got in the first stage treatment, whereas non-responders are randomized evenly between 2 options in that example. So that's why responder and non-responder gets different weightage when you compare these regimes. Okay, so once you know these weights, you can find you can estimate the regime means by this weighted averaging. And also for large samples, there's a variance formula based on the weights. So you can compute the mean and variance of each of those embedded regimes, which you can then compare. Right? Once you know the means and variances of all these different embedded regimes, you can make a comparison straight away using classical statistical approach, meaning significance test and so on. Okay. Primary analysis, there is this paper, nice paper, talking about these different aspects of it, and very accessible text. So this can be a comparison, depending on the research question, it can be a comparison of 2 or more groups corresponding to 2 or more DTRs embedded in the SMART or components of those DTRs. Standard methods of analysis involving those means and variances, and people have used, in fact, this paper have used SAS proc gen mod for that, ANOVA type of comparison. Now we talk a little bit about the sample size for different research questions, right? So this is something that is a recurring theme in anything related to trial design. You have to talk about sample size. So if your primary hypothesis is that averaging over all the secondary treatment options, the initial treatment B mod is as good as the initial treatment medication, right? You are basically comparing these 2 things. So then sample size formula is exactly same as that for a 2-group comparison of RCT, right? So you combine everything red here and everything green here, and then it will be comparison between the 2. Then there is other scenario where you may hypothesize that among non-responders, an augmentation is as good as intensification, right? So across both the initial treatments, you go to the second stage and see you combine people who have an intensification versus people who have got an augmentation, right? So you again combine the 2 red arrows and the 2 green arrows and then make a comparison. So you are using only the non-responder. So what is the implication of that in terms of sample size? Then you are not using the responder group of people, right? So you are only focusing on the non-responders. You are combining across. So your final sample size will depend on the non-response rate, right? That's how it will be inflated compared to a standard RCT. That's the inflation factor. And then the scenario 3 is hypothesized that one particular DTR, in this case the red DTR, is as good as the green DTR, the other one. You can have other combinations of DTRs, but in this case you are just choosing 2 embedded DTRs. So this sample size formula involves a 2-group comparison of weighted means, right? So like the ones I showed earlier based on that inverse probability weighting, you will have comparison of 2 weighted means, and again this will depend on the non-response rate. So this non-response rate becomes a very key factor in this sample size. So the sample size formula, in addition to the classical ones, the Cohen's effect size or all these things, in addition there will be an extra term which is the response non-response rate. And once you can input that, straightforward. The formula becomes straightforward. Okay. So again, in that particular context of a continuous outcome like the teacher-rated impairment rating, we have computed the sample size requirements for these 3 different scenarios. And 3 different scenarios. Scenario 1 is basically the one where you are treating it as a standard RCT and forgetting about other things, making everything secondary, right? Primary comparison. So here in this case, for different Cohen's effect sizes, according to Cohen's d, which is the comparison of, which is the difference between the 2 means divided by the standard deviation, 0.3, 0.5, 0.8. For different scenarios, you are getting this kind of a sample size. And this is exactly what you would need for a standard RCT. That becomes the sample size requirement for a SMART as well. But then if you want to be a bit more ambitious, you want to really answer more questions of relevance, then scenario 2 and 3 will come in, and then sample size requirements will go up accordingly. I think scenario 2 may be a bit more ambitious, but then scenario 3 is probably more realistic. And ultimately is about the sequences. Yes? Okay, because scenario 2 is here only you are focusing on only these people, only the non-responder group of people. You are throwing away a lot of information. Yeah. Right. Yeah. So among the non-responder, which one is better or which one is comparable, right? So better, yeah. Right. Okay. Right. 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 That's right. Yeah, exactly. Yeah. And in fact, if everyone is a non-responder, in an extreme scenario, if everyone is a non-responder, then you are good. Then it becomes an RCT, right, essentially. Okay. So scenario 3 is in between. It uses information from both responder and non-responder. Even though it's a comparison of the sequences, it doesn't throw away the information from responders. It uses all their information, but it wants to answer a bigger question about the whole sequence. Right? That's why it's scenario 3. Yeah. So here you are comparing 2 DTRs, 2 pathways, not only the non-responder or only the responder, but it's 2 pathways, right? The red and the green 2 pathways, right? Yeah. Or you start with the medication and then continue medication if responder, or if non-responder you give the, yeah, right. Yeah. You start with medicine and then medication and then you continue one. Right, exactly. Yeah. But look here we are not completely throwing out information from responder. We are using all their information. It's just that it's a harder question that we are trying to address, and that's why we need more sample size, right? So that's why the sample size requirement for scenario 3 is in between scenario 1 and 2. Scenario 2 is more extreme because it throws away information from responders, right? Whereas here in scenario 3, it's not throwing away information, but it's basically trying to answer a bigger question than scenario 1. Okay. Some other comparisons, but I will not go into the details of that. So you might want to compare regime D1 and D2, right? Earlier, the scenario 3 I talked about is D1 and D2 and D3, right? D2 and D3. So basically, what that means is that there is no common people between the two. There is no individual that is consistent with both regimes. They do not share a path, right? Whereas if we want to compare D1 versus D2, I just remind you one more time what is D1 and what is D2. Yes, so this is D1 and this is D2. So you see, they are essentially same except for this part, right? So they share the same group of responders. Two regimes share the same group of responders. So they have common element, meaning they are correlated. These two pathways are correlated. They do not have separation. Yeah. Yeah, directly out of randomization, right. Subset of what you have randomized, right, yeah. For the sample size, I mentioned 3 scenarios. Here by scenario, I meant what kind of question you are trying to address, and based on that, your power sample size calculation, yeah. Yeah. Question, yeah, trying to address, right. Right, oh, right, that's right. Okay, so you see and now we are talking about comparing shared path DTRs versus distinct path DTRs, right? And these are different, they have implications. Because in a shared path regime like D1 and D2, they share the path, you see? You see B mod and B mod if responder, that is thing. The only thing different is here for the non-responder. So responder part is same, so there's correlated data. So that will have implications for your sample size. Yeah. Yeah. Mm-hmm. No. Actually, the other way. The distinct path is better. Because then you are keeping them separate, no common people between the two groups. That means no correlation. But if you are interested in comparing shared path, your sample size will go even higher because these are correlated, right? Yeah. Because correlation will inflate your variances of those things, right? Okay, so this D1 and D2, okay, they are sharing that. Okay, I already talked about that, contribute information. Okay, specialized methods are needed to account for reusing their information. So, okay, the analysis will be little more complex. And the sample size requirement is already clear, right? So, okay. And then alternatively, you might also want to do some kind of ANOVA type of analysis, D1, D2, D3, D4, everyone. You compare all of them, right? And to see whichever gives you the best one. So this requires more specialized methods to account for both the multiple comparison, as in ANOVA that we know about, and also the reuse of data because of the correlation that I mentioned. So these things need a bit more complexity, but can be done, right? So I'm not going through the details of that. Okay. Okay, again, in the interest of time, I would not talk much, but there is also a version of sample size calculation for survival type of outcome, time to event outcome. Because so far I only talked about the continuous one, but, and this is based on, again, the same ideas of inverse probability weighting come into picture, but you have to do the tests for survival, like the weighted Kaplan-Meier or weighted log rank test, etc. But this weighted thing will always be there because that inverse probability weighting will feature in. Okay, in interest of time, I'll skip that. Okay, some more comments about the time to event outcome. It's also actually, there is a web app where you can compute the sample size. So now, these days, there are a lot of web apps or R packages to use for sample size design for this smart design. So it's not like you always have to talk to me. You can just go to the web and find it. Okay. All right. Just coming back, I'll just make a few comments about how smart can be applied in the mHealth setting. Okay, I think these are some pictures. Okay. In the interest of time, I'll just skip those. Just motivating how mobile health is useful, etc. I'll just skip. Okay. So this is some problem that we worked here locally. So I just want to share a bit about that. So mHealth interventions for diabetes management, and in Singapore there's a lot of attention from the government about diabetes and so on. So here, just as a background, treatment for type 2 diabetes involves diet, exercise, oral medication, and insulin injection for more advanced cases. And initiation of insulin in insulin-naive patients who are not used to, who are just starting insulin, traditionally involves multiple visits to a physician to adjust insulin dose, which can be costly and time-consuming. We have to make multiple visits. And delay in scheduling can result delay in achieving glycemic control. And so self-titration was something that people thought that may be helpful with the help of some app, mobile app. But many patients hesitate and express uncertainty. So there was this smartphone app that was developed here in Duke NUS and Singapore General Hospital with an inbuilt algorithm to compute daily insulin dosage based on lowest of the previous 3 fasting blood glucose readings. And so patients need to measure their fasting blood glucose daily and input into the app. And based on that, the app will give some recommendation. And the name of the app is Diabetes Pal. Okay, and the feasibility of that was already tested and published, but it was a very small sample size, only 66. Okay, so one thinking from this dynamic treatment regime context, smart context, is that what can be done next with that. So not everyone in the population is good with technology. So some may need human intervention, like help with a human nurse, but that adds cost to the system. So perhaps a stepped care approach involving the app may be cost effective, and so maybe start with a low cost, low intensity intervention like the app, and then only step up to a high cost, high intensity intervention like a nurse, only for patients who show early signs of non-response, who do not really respond to the app, right? So it would be interesting to study if the stepped care regime is almost as good as or non-inferior. So this is another concept I'm bringing in here that was not considered explicitly in the traditional smart literature, but that is very common in the classical clinical trials. In clinical, one drug is non-inferior to another one. That's non-inferiority testing. It's just for those that are not familiar with this concept, is basically the way you formalize the statistical hypothesis, how you write it down, how you test it. So here is just that stepped care regime is almost as good or non-inferior to the more aggressive and resource-intensive regime, which is the nurse, which is sort of the control, the standard of care, but it's resource-intensive. So if it is actually non-inferior, then the stepped care regime should be selected. This can be investigated in a SMART. So this is a trial design that we conceptualized. So nurse group serves sort of like a control, and we do not deal with it, we do not interfere with it. So that's that. But then app can be done, app approach can be amended with this smart design idea. So responder will continue, but the non-responder will potentially get either nurse or nurse plus app. So nurse plus app means physically a nurse will help you navigate through the app maybe one time, so that it does not really require the full involvement of the nurse all through the process, but some education by the nurse to use the app, and then they will get it from there. Okay, so using the method, using the notations as before, you can write 3 embedded regimes, D1, D2, and D3, because here nurse 1 is not re-randomized, it's just is the control group, right? So D3 is the active control, and D1, D2 are the 2 stepped care dynamic regimes that you want to compare it with. And non-inferiority testing, for those that are not familiar with it, generally the goal is to show that the efficacy of the experimental treatment regime when compared to an active control regime is not below a pre-specified non-inferiority margin, meaning how much is your tolerance for a bit less effective, but because it saves cost and other things, you might be tolerant to a little less effectiveness, but how much you are tolerant to, so that part is the non-inferiority margin that you have to specify. In practice, the non-inferiority margin is the maximum clinically acceptable difference from the active control on average that researchers agree to accept in exchange of the secondary benefits like the cost and side effects, burden, etc. Okay, so this is how you can write the null hypothesis and alternative hypothesis, that mu of D1, here D3 is the control and D1 is a comparator, is a dynamic regime here. So the null hypothesis is that mu of D1 is less than or equal to mu of D3 minus theta, where theta is the non-inferiority margin. It's below theta from the control group, whereas this one is in between, within theta margin of the control groups, active control groups mean. So if you reject the null in favor of the alternative, that means you call it non-inferior treatment. Yeah, the choice of theta is critical and depends on statistical as well as beyond statistical, more clinical judgments. And the test statistics is the mean difference, and you have to compute the variance of that using the Murphy's formula that I have given earlier, the large sample formula. With all that, you can then, after you specify the hypothesis, then relatively straightforward, but here you remember, you have to note that the test statistic involves the theta. In the standard superiority testing that we are used to, there is no such thing, it's 0, right? So it's only this difference divided by the standard deviation, but here you have to also include the theta, and then you can reject the null hypothesis and conclude non-inferiority if this Z D1 D3 is greater than Z alpha, the cutoff point. This is a one-sided test typically, and deriving the exact sample size formula requires large sample approximations and assumptions. I'm not going through the details, but one thing is that given a postulated effect size delta, a difference between the two, the required sample size depends on the difference between theta and delta as opposed to their individual values separately. Okay, and we don't have a real trial yet for this design, but we did some realistic simulation using some synthetic data, and we used data was simulated from the actual pilot study. That was a real study, and we simulated the Y values as negative of the HbA1c, and the response rate to the app and response rate to the nurse, these were collected from the Deloitte Global Mobile Consumer Survey. So you fix the response, non-response rate to the interventions according to those, and based on that and by simulated data from the pilot study, we computed the means, variances, etc. And here is just the numerical example that by changing the theta, the non-inferiority margin, the result will change. So the choice of theta is very critical, and there is no straightforward answer to answer that question, but one has to be careful and consult the literature, what is clinically meaningful, etc. Okay, so that's one application in mobile health, and even though it's simulation, it has some realistic elements. And then the other comment I want to make here, unrelated to the non-inferiority, is another thing, the adaptive randomization that we mentioned earlier. And earlier I said adaptive design, classical adaptive design is different from SMART. But here is an attempt to combine the two concepts. And here is a design we call SMART AR, SMART with adaptive randomization. And what is the motivation for that? So motivation is that the technology is driving the apps and so on. They evolve very quickly, so interventions using mobile devices must be evaluated and disseminated very quickly. Otherwise, they will lose relevance. Some other competitors will replace. Right? So in that case, so you have to basically disseminate the results as quickly as possible so that at least some people get benefit, get the results out of that trial. So that means why not you try with some of the later participants in the trial itself, because if you delay too much, then by the end of the trial, when you complete everything, then there might be a fewer group of people who might be interested in it anymore. You might lose relevance. So why don't you disseminate it quickly? As you accrue data, you just give it to them. So that's what drove us to consider this adaptive randomization within a SMART. And in the mHealth context, we particularly found that useful. And this is also ethically appealing even in a non-mHealth context, right? So even if there is nothing about mobile, but just because you can quickly reach your audience, you are taking the welfare of the trial participants into your design. That's why it's also ethical. But at this point, it's not quite known how best to do this adaptive randomization. We had some ideas, we proposed some things, but not any optimality attached to it. Okay, so that's the design. Finally, I'll spend a little bit of time, very little time on the estimation of optimal TTRs. I think this is the question that was coming earlier, how do you analyze data? So here the goal is to find the optimal treatment sequence for each individual patient by deeply tailoring on their time-varying covariates and intermediate outcomes. And so this is not, so we have already conducted the trial. At this stage now we are talking about a situation where we already have the data, already done SMART or SMART-R or whatever you have wanted to do. But now you have all the covariates, all the time-varying covariates, etc., baseline information. But how do you best incorporate that information to specify and estimate the best outcome? And in terms of the earlier notations, how to incorporate that best psi parameter that are thresholds for the rules and so on, right? And in this case, we will talk about this Qlearning, this version of Qlearning, which is essentially a stage-wise regression-based method. And before we go into the method, I just want to say that there is actually more than one. This is one of my earlier students who did our package, but again, there are many other packages now to conduct Qlearning. Okay, so Qlearning, a little bit of background. Originally started with Watkins in reinforcement learning, and is the Murphy's paper in 2005 that basically proposes this as from a different angle as a generalization of least squares regression to multi-stage decision problems. And since then there has been many versions adapted to different situations, different outcome types, etc. The good thing about this is relatively easy to understand and implement and forms a good basis for more complex approaches. Since this is related to regression, a lot of people understand this, at least on the surface. But the real intuition comes from dynamic programming, which dates back to the 1950s. And in case but the dynamic programming approach, the classical one that basically assumes that the multivariate distribution of the data is known. So in the jargon of reinforcement learning or control theory, control engineering, those things, basically you have a known environment. You know the transition probabilities from one state to another, etc., etc. So you basically have the full data distribution. But that may not always be realistic in the medical context. And so Qlearning is not an exact dynamic programming, but it's an approximate dynamic programming. It uses that idea. Okay, so just a recap of the data structure. We still have the O's and A's, and we construct these histories H, and Y is the outcome. Okay, and so just focus on 2 stages, but it can be extended to any finite k stages. So here, instead of moving forward in your decision making, it basically moves backward in time to take care of, that helps taking care of the delayed effects of treatments. Yeah. What is the problem to solve? Right. So the problem here is you want to estimate the best treatment sequence for every individual patient based on their covariate data. Remember, when we talked about the trial design, it was very crude in that sense. It was only responder and non-responder, and that's the only where you are doing some kind of personalization, right? Because it's a trial design, you cannot go into this granularity. But now that you have completed the trial, you have the data, but from the trial data you have not only collected their responder, non-responder status, but you have also collected many other covariates, right? So now you have data on all of that, and now you are doing like a subgroup analysis. You have all that information and you are throwing it into some kind of a regression model to find out for specific subgroup of people what is the best treatment. Right, yeah. Right. Yeah, so now I'll just talk about 2 stages, but the same idea can be extended to any number of, finite number of stages, right? But basically it's a stage-wise regression, as I will illustrate, yeah? It can be, okay. So so here this is basically moving backward in time. This is backward induction, right? So so you can start with the end result, but in the previous stages you have to create sort of projection at that stage, or if you use statistical or causal inference language, then it's a counterfactual kind of outcome. But you have constructed outcomes, not the observed outcome necessarily. Right. Yeah. Right. So if you have like a step count, right? If you have some intervention and you are collecting steps, right? So step count you can add up. So if you want to apply this version of Qlearning, you can basically add up all the step counts for the intermediate stages and get your overall grand total of your steps. That could be your final outcome. Or like some of the examples here. Okay, so in the ADHD example, it can be the teacher-rated impairment rating, right? So it's a score, numerical score at different stages. You can have an average score over the entire. So you can construct that end of. So it doesn't have to be measured strictly at the end of it. So it can be an accumulated reward over the entire study period. Okay. Okay. So here we define the so-called Q functions. Q for quality of action, quality of treatment. So you define Q2, the end stage Q, end stage quality of action, end stage objective function, whatever you call it. Q2 of H2 and O2 as the conditional expectation of Y, Y being the composite overall outcome, end of trial outcome, and then given the history and treatment. So that's straightforward, but then the first stage, Q1, you are not looking at some kind of Y1 necessarily. Not just the immediate outcome that you are looking at. You are looking at the projection of the delayed outcome altogether. So basically, it's saying that is the max over A2 of Q2, given the current history and action. So given the current history and action, what would be my best outcome if I behave optimally in future? So that's not a real outcome, it's a constructed hypothetical outcome. From now on, given my history and action, from now on, whatever happened has happened, but from now on, if I behave optimally in future, what would be my best outcome, right? So that's maximum of Q2 over A2, my future actions. You are taking an expectation of that quantity, right? So this is not new, this is basically the dynamic programming idea. And once you know these two Q functions, one you can enumerate, evaluate these two Q functions, you can basically construct the DTR, the decision rule, as the argmax of Qj. So whatever action maximizes my Q functions at each stage, that would be my decision rule. So these dj's will constitute my final optimal regime, right? But the question is, what if the true Q functions are unknown, right? So these were the dynamic programming in its original version. It was constructed for more engineering type of setting where many of the laws are driven by physical laws, right? So you have a very good understanding of the environment, of all the distributions, so that you can exactly compute these expectations. But in the medical context, it's very different, right? It's very hard to specify all the distributions. So you have to use some other things, and basically because your objective functions are conditional expectations, you work with regression, right? That's what is being done. Okay, so basically you turn to semi-parametric methods in general, and one approach, the simplest approach, is doing regression models, which is Qlearning, but you can even go less parametric. You can make it even more semi-parametric or non-parametric. And if you want to make it fully non-parametric in that sense, you can do like a machine learning approach fully. So here I will give an example just to help you interpret certain parameters and so on. I'll only talk about linear regression for the Q functions, but you can also use something like a support vector regression and so on. So that way it becomes fully non-parametric, fully data-driven. Okay, so Qlearning with a typical implementation k equal to 2. So for each stage you postulate a linear regression model, and here I make a distinction between these two terms, beta j transpose hj, which is sort of captures the main effect of the history variables, all the individual covariate kind of variables. Whereas the second term, psi j transpose hj aj, that is an interaction term between history and action. And that is the one that is critical for individualization, right? Given a certain covariates, how your treatment affects your outcome. Right, yeah. Not just very, also the correctly identifying the model, right? So if you drop that model entirely, then Q would be probably misspecified, right? The model itself may be misspecified. So you try to adjust for all the variables that are there potentially. Yeah, it would not be big deal, right? It would not be big deal if the individualization is right, but policy right might be right, but it might be also the case in some situations that if the model is misspecified, it might also imply that the policy will be wrongly estimated, right? So, but if that's not the case, then you are fine. Right. Right, yeah. Sure. Yeah, and in fact, there is a method called A-learning, advantage learning. So it basically models the advantage you are getting, which is basically this part. So you are actually hitting the right question. So it basically focuses on only that part. And you just do whatever you want to do with that one. And there's a way, it's a little more complicated than this, so I am not presenting it here. But it's essentially exactly answering your question. So it is more semi-parametric. It does not worry about the correct specification of these main effect terms. It only focuses on what really matters from a personalization, from a policy point of view. Okay, so in a two-stage setting, at stage 2, you regress the final y on h2 and h2 times a2, the interaction terms, to obtain your beta 2 hat and psi 2 hat, all the parameters in the stage 2. Once you have that, then you construct your stage 1 pseudo outcome. So it's basically the sample version of this quantity, right? So you have to construct this max of Q2. So basically you are constructing max of Q2 hat with the beta hat and psi hat. That's what you are constructing. That's the pseudo outcome. I for individual. For every individual, I equal to 1 to n. Every patient. Yeah. Yeah. So earlier I kept it simple, but I think here I'm just using the I. No, the averaging kind of thing comes in the estimation. So beta hats and psi hats, they are based on all the patient's information. Yeah, but I think you are right. So maybe here in this slide, maybe I could drop the I actually, just to avoid confusion. But it's basically the estimation takes care of all the I's. Yeah. So those are not so personalized in a way. Beta hats and psi hats pulls across all the data. But personalization comes through the covariates, right? So this is your pseudo outcome, and again, if you use the causal inference language, then it becomes a counterfactual outcome. This is not a factual outcome, but what would have happened. And then once you construct the pseudo outcome, you regress this on the stage 1 variables to obtain the beta 1 hat and psi 1 hat. So that uses information from all the n subjects. And once you have estimated the size 2 and 1, basically you know the policies, you know the rules. Stage 1 pseudo outcome is you already, okay, stage 1. So that means you have already conducted your stage 2 regression done, right? Stage 2 regression done. So that means you have already got your beta 2 hat and psi 2 hat, right? Okay. So then you have your Q2 function. You have already postulated a model for that, right? And in that model, the parameters, unknown parameters were betas and psis, right? And then now that you have already conducted your stage 2 regression, you know these betas and psi, you have estimated them. So you plug in those estimated values. So you can actually have known values. Now for Q2, you have known values of betas and psis. All that you don't know is your H and A, right? And so for any given history, now you can evaluate that for every possible value of A. And then you take the max over all the A's. For every individual, so that means, so this is for every individual, you have the common betas and psis, right? You have the model schematic. And now, for every individual, you have a history. You plug that history in also, right? So all that remains is the action, what action to take. Largest. Take the correct action. Assuming that model, you take the correct action. Right, exactly. So, and that's basically, as I said earlier, right? This is what is there, right? We are trying to create a sample version of it from the data. So once you have that, your estimated DTR, DTR by the way is same as a policy. DTR is basically a policy, right? So you're trying to estimate that model dependent policy. You have that argmax of the fitted Q function as your DJ hat, and In this case, if you have a binary -1, 1 kind of coding for treatments, then this becomes a sign of this linear combination psi j transpose hj, right? And note that ultimately in the policy, there is no role for beta. It's only the psi, right? So beta is, as you mentioned earlier, Joseph, is basically for reducing variance and model correct specification, etc., but ultimately the policy is dependent on the psi. So that's the critically important parameter that I'm interested in. But betas are, in a statistical language, betas are nuisance parameter that sort of helps you do what you want to do, but ultimately not of interest. Okay, some remarks about the Qlearning. Is easy to implement in standard software because it's essentially regression. You just have to have a code to construct that pseudo outcome. Other than that, it's a regression. But it has some limitations, of course. It's not robust to model misspecification. So your policy is as good as your model, right? So if you postulate a wrong model, then you may not be protected. You might estimate a wrong policy. And also a lot of work is on continuous outcome, but relatively limited results for discrete type of outcomes. There is some work on survival, time to event kind of outcome as well. So it's growing, but there is still not foolproof for the discrete type of outcome yet. And I already mentioned A-learning, which is more semi-parametric, meaning it only focuses on that psi part, not the beta part. That's one. And then there is this thing called outcome-weighted learning. That's not a regression approach at all altogether. It's a different approach. It has stronger connection with classification. So it basically considers a weighted classification kind of an idea. So in a classical classification, we worry about the misclassification rate. We want to try to minimize the misclassification rate, and because the misclassification rate in itself is a non-convex optimization problem, people typically approximate it with different surrogate loss functions. And in fact, some of the very popular and off-the-shelf machine learning methods like support vector machine or boosting or all these methods, they are essentially some approximation to that non-convex loss function in classification. Here, it basically creates a weighted version of that misclassification rate, and then approximates using one of those surrogate functions. And in particular, in this outcome-weighted learning approach, they use support vector machine to approximate that thing. But this is not a regression kind of approach. It's a more direct policy search-oriented approach. So for a class of policies, for a class of regimes, class of rules, you construct the value of that approach, that policy, and then you search over the space of rules directly. Whereas this regression kind of approach is more indirect. It creates a model for the outcome and then tries to find a DTR that works best, but that's model dependent. Whereas that one, that is policy search, and that's non-parametric. So, well, this is more recent. This is good in that sense. It's not so model dependent, but it also has variability, right? So, relatively non-smooth, whereas this one is more smooth approach. You have a linear model, etc., etc. So there are pros and cons about these different methods, but that one slightly more complicated. I'm not going into that. And later in this workshop, we will have Yingqi Zhao from Fred Hutch. So she was the one who first developed the outcome-weighted learning. So I don't know whether she will be talking about that or not, but if you are interested about that idea, that approach, you might talk to her. So that's that. Okay. It's already 12. Maybe okay, just quickly just mention that why we move through stages as in Qlearning or A-learning, whatever, stage-wise regression. Why not run an all-at-once multivariate regression? This is another question sometimes people face, that why not I throw everything in one big regression and go ahead with that. So there is some phenomenon in causal inference that does not allow us to do that, basically called Bergson's paradox or collider stratification bias, which basically says there might be non-causal association even with randomized data when there are stage-wise things leading to biased stage 1 effects. And so that's a causal diagram for that. I think in the interest of time, I would not go into details, but if you're interested, talk to me later. Okay, real quick, one example, that Project Quit, the smoking cessation study I mentioned earlier. This was conducted at the University of Michigan. This is a pre-mobile health era, but this is still aligned with that theme. It's an e-health, electronic health, web-based behavioral therapy for smoking cessation. And here we did a Qlearning type of analysis. Stage 1 covariate was education, less than high school versus some college. And the intervention was tailoring of a success story. It was behavioral intervention given through stories of successful people who quit smoking, etc. So whether that story would be highly tailored to your personal characteristics, the character in the story will be highly tailored to your personal characteristics versus more generic. That was the intervention. And in addition to everyone getting free nicotine patch, etc., etc. So pharmacological aspects of smoking cessation were taken care of by patch, but then the behavioral side was addressed through the intervention. And stage 2 covariate, some quit status at 6 months, and months non-smoking over the next 6 months, etc. And there was also some follow-up intervention at stage 2, and final outcome we looked at was months non-smoking over the 12 months. So that way it adds up, right? So how many months you did not smoke, so that adds up. It's not like something you abruptly observe at the end, where it adds up over the study period. So that's the schematic of the study. Okay, and then we basically analyzed the data. In the stage 2, we did not see any effect. And in stage 1, there was quite weak in a usual statistical significance sense, but we still found something interesting between tailoring of treatment by education. And this was actually meaning that the highly individually tailored level of story was more effective for subject with less education. And that was quite interpretable, actually. So, more educated people are more skeptical, they don't really believe in stories and so on. But in the low education group, if they can really connect to the hypothetical characters in the story, that makes a difference in their behavior change. So that was supported through, cognitive behavioral therapy, theories and so on. So that was good, and that was kind of expected. That's the most important thing. And it was also consistent with standard logistic regression analysis of one-stage analysis. So without going through any complicated analysis, without going through reinforcement learning, just a standard logistic regression also found that result. So that way it's not spurious. We believe that this is real. Okay, you had some question. Oh, yeah, I didn't want to go into that details, but we have papers on that, and that was basically, that was a bootstrap, but ideally it should be M out of N, but I don't remember whether this is a later analysis or the earlier analysis, because when we first published it, at that time M out of N was not there. So it might be the standard bootstrap, but later on we worked on the M out of N bootstrap. So I don't want to open that can of worms here. Right? Yeah. Okay. But yeah, sure. That's a very valid question. Yeah. In the second stage, it did not matter so much because that was not so tailored in the first place. Second stage was booster prevention or control. So basically everyone, so irrespective of responder, non-responder status, everyone who remained in the trial till then maybe in the booster prevention is just reminding people. It's not like the stories or anything like that. It's just some reminder that, okay, smoking is not good for you and do this and that. So general things versus control is nothing, that kind of stuff. Yeah. Right. No. So here it says that if you are a low education group, then you give the tailored intervention, and then you do your booster prevention, whatever. If you No, I think we also, when we did a more finer analysis, we saw that it actually lowers your, because they are probably getting bored or something, Okay. Yeah. Better to give the generic one, and then if it's a low education, then give the tailoring. Yeah, right. Yeah, right. That's right. Yeah, so it backfires. Yeah, people get bored or whatever. Or in other words, just it's not gonna work much for them anyway. Yeah, they knows everything, but and one thing. Yeah, right. Yeah, backfires. Right. That's right. Right. That's important. In fact, more recently we have conducted, one of my postdoc actually conducted some analysis with a different outcome in this study. It was like the number of quit attempts throughout the study period as an outcome. And even in that one, we specifically saw that it actually backfires. Yeah, so I think it's important to note that the policy is different for different groups. Yeah. So that's the only personalization we are getting out of this analysis. But so many, yeah, sure, right. Doesn't matter, right? Yeah. Yeah, that's right. Yeah, no, so, okay, so when the trial was designed, the primary outcome they looked at was actually the cessation in a very small window, whether or not you smoke in the last, 7 days or whatever. That's the kind of the standard thing. But then that was how it was designed. But later on in the analysis stage, we looked at many different outcomes, and here we looked at the number of months not smoked, because it appreciates the fact that people relapse in smoking, a lot of relapse, right? So people come. So that's why over the 12-month period, how many months you have been smoke free versus not. That was a more, what should I say? It's not like a very immediate kind of an outcome, because you may come and go out of smoking. But yeah. So what would be your recommendation as an outcome, as an endpoint? Okay. Yeah. Yeah, it's very hard. I mean, it's very hard. Long term, how do you keep them away from smoking? It's not clear, but at least this. Anyway, so that's what was done. Yeah. Okay. Yeah, I think that's basically all. Just summarizing that SMART is a cutting-edge trial design, formalizes the sequential decision making relevant for chronic conditions, and does not necessarily require a lot of sample size. It depends on the research question. Useful in mHealth, as I have shown some example. Non-inferiority testing can be done here, very appealing from a cost-effectiveness point of view. Analysis method exists for continuous binary time-to-event data coming from a SMART, and in particular, you have seen this Qlearning here, but there are also versions of Qlearning that is relevant for other outcome types like survival and so on. Softwares are there, and still, I mean, you know, it's getting more and more saturated, but still there are lots of open questions and people are working on it. So, yeah, opportunities for statisticians and data scientists. Yes? Okay. Yeah. That's right, yeah. Uh-huh. Yeah, I don't think there is no theoretical reasons like, okay, if you do that, you will not achieve a certain performance. I don't think there is any such thing. It's just that in the clinical settings, it's kind of difficult. But having said that, I think there is some work. I don't know about any recent work that you guys are doing, but maybe it's a few years back. I think I saw some paper where, in fact, Mary Davidian was a co-author. I think there are probably some other people, either at your university or somewhere nearby. Anyway, so I think they did something on HIV modeling, etc., etc. So that sort of did that. So you might want to look. I don't remember the exact citation of the paper now, but I think I've seen something. Mary was on it. Yeah, I think it was on HIV. So they actually tried to model the dynamics of the disease and so on, and then applied something. And it was not in a stat journal. I think it was probably more towards like mathematical modeling, that kind of stuff, that kind of journal. Yeah, that's another issue. But again, having said that, if you can make some good feature construction, right? So if you can summarize in a good way. That's right. Mm-hmm. Right. Yeah. Yeah. Right. Right. Okay. That's right. Yeah, that's right. 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 That's right. Yeah. Right. 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 What's the cost? Right. Yeah. Yeah. I haven't seen anything concrete, but I think that's a good idea actually. In fact, in the cost effectiveness analysis, people always talk about this incremental cost effectiveness ratio, etc., right? So incremental cost effectiveness is basically difference in the cost of two treatments divided by difference in the effectiveness, like the reward classical sense, right? So you can, divided by the difference in cost, difference in the effectiveness of the two treatments. Like incremental cost effectiveness ratio. And you work on that? Yeah. So you can speak with her, yeah. She works in SCRI, the Singapore Clinical Research Institute, right? You're still there, right? Yeah, so I think they do that kind of stuff, yes. Yeah. 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 Right. 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 Yeah, exactly. Yeah. Yep. Yeah. Exactly. Yeah. Yeah. In fact, Joseph, the kind of studies that you are doing, I think this is something to really seriously think about. To collect data on that also. Yeah. 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 Right. That's right. Yeah. Yeah. Okay. Yeah. Right. Yeah. Yeah. Yeah, that's right. Right. Sure. Yeah. All that. Okay, so I have a book. If you are interested to know about these methods, you can come. Okay, here is my email. If you have questions, you can always ask me. Okay? Yeah. Infinite Horizon, I think Markovian, and there is also something called actor critic. Do you know about that? Actor critic? Yeah. 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 Other thing, actor critic, yeah. So yeah, a lot of different reinforcement learning methods can be done, and so this is one version of Qlearning, but the original Qlearning is actually Infinite Horizon. So I think there are a lot of things you can do. Yeah, it's a bit hard. Yeah. Okay, so are you talking again? I always ask this: are you talking about the trial design or the analysis? Smart design. Okay, so you're talking about the design, right? Yeah, right. So okay, my answer would be that if you want to do a smart in the pharma setting, probably consider the non-inferiority setting, because that way, pharmas are very concerned about business loss, where some other treatment is, because we are always talking about the sequences, and it may not be the case if it's all the treatment components in a sequence are manufactured by the same pharma, then it's fine, right? Then not a problem. But if there are components that are from different pharmas, or the competitors are for different pharmas, so then that becomes complicated, right? So I think a first step could be consider non-inferiority testing, so that no one really is inferior in a setting. I think that might be more acceptable. Right. Right. Yeah, exactly. Yeah. Yeah. No. Yeah. That's right. Basket, I mean, I also, thought about it sometime that, okay, maybe, on the basket or umbrella settings, it might make sense, but I don't know of any real study which was done with the smart idea in any of that. But if any of you can influence any PI, I think that would be good. That would be good. But again, the question is whether, no, so the first line, second line, that is very natural, but are they all developed by the same pharma? That's the right. Yeah. 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 Possible, right? Yeah. Right. That's right. Yeah. So again, I mean, I have also spoken to some pharma people, and like you said, some people actually appreciated the ability of this taking care of first line, second line kind of treatments, and it makes sense, and basket, umbrella. So even I have spoken with some friends in pharmas, but I haven't seen any real trial yet. So that's the bottom line. So if you can influence people, that's great. Yeah, in principle, other than the competition with other manufacturer, other pharma, that it should be fine. In terms of methodology, it should be fine. Anything else? Okay, if not, then I'll stop here. I already taken a lot of your time.